researcher in the Learning and Intelligent Systems Research Lab at the Technical University of Berlin. In Berlin, he is working on physics-informed robot learning. I kind of wish Cyrus was here, but anyways. And then previously, during his doctoral research, he worked on continual learning to help robots learn new skills without forgetting past knowledge, which included work on using continual learning from demonstration. So now we're going to hear a bit about his research current and past. And thank you again for joining us.
Thanks for the introduction. Yes, so hi everyone, I am Shantan and I've just started as a postdoc in TU Berlin, so the postdoc game is still very new to me. So today I'll mostly be talking about things that I did during my doctoral studies in Innsbruck, and this is on continual learning, specifically for robotic manipulation. All right. Yeah, so as humans, we have this amazing ability to keep on learning throughout our lives, right? Like, as we grow older, we learn new things, and the most important part of this learning is that when we learn something new, we do not forget what we've learned in the past. So, learning a new language does not mean that we forget our native language, or learning a new recipe doesn't make us forget how to make something that we learned at the beginning. But the predominant view of machine learning is that we gather data and we train a model, and once a model is trained, we deploy it, and that's it. And the problem with this is that the data might change, the world might change, and that would mean that we need to retrain the model, but this is not really addressed in all situations. A more adaptive view on this kind of setup is what is required, particularly for robots, which in the future we hope will be, seen everywhere. And if they are to inhabit these human environments, it just means that robots need this ability to not only learn once, but learn many, many times in an open-ended way without forgetting or, without erasing all the knowledge that was gathered before. So this is mostly the crux of, like the main motivation behind what I was trying to do. So here's a brief breakup of the talk. So I'll start by talking about a few learning scenarios. So what I do is I try to make sense of what are the different kinds of scenarios in which continual learning makes sense. And I divide these scenarios into two very broad groups called CL tasks and CLNs. I'll elaborate on those things a little later. But yeah, first I'll start by describing what these scenarios are, and then I'll dig deeper into each scenario. I'll cover a couple of papers for the first one and one paper for the next one. And I'll end with some thoughts on future work and what I'm working on at Berlin currently. Okay, so when I talk about learning scenarios for a robot, this can mean a couple of different things, right? So on one hand, we might have tasks which are fundamentally different in the sense that the objective of what the robot is trying to do is different in each of these tasks, right? So let's say a robot wants to paint, or it wants to build something out of Lego. These are very different tasks with different objectives. And these kind of scenarios I call CL tasks, because here the difference is in the basic task that the robot is doing. On the other hand, we might also have continual learning scenarios where the robot essentially does the same thing, but things change either in the tools that it uses or the objects that it interacts with, or something that really affects how the task is performed. But in this example, in all of these four tasks, the robot is just performing the cutting task. It's cutting something with a knife. but then the knife might be bigger or smaller, or the object that it interacts with also changes. So these kind of scenarios I call CLNs, because here the distinction is mainly between the different, like the distinction is in terms of the environmental factors that are changing. And so first I'll start off with CL tasks, and here I'll talk about a couple of papers which deal with this thing called continual learning from demonstration. So learning from demonstration or imitation learning is pretty straightforward. We start with some demonstration of a task provided by a human. We gather the demonstration in some data set. So in this example, it's the trajectories that the robot executed, and this is used to train some kind of machine learning model, which then later on is used to help the robot perform that task. And this is pretty straightforward. It's quite easy to do. And continual learning from demonstration is essentially just starting from this same setup where the human shows how to do something, the robot learns how to do that. But then it keeps on adding newer and newer tasks. So in the next iteration, the human comes and shows something new. And here the objective is that the robot should be able to perform both the first task as well as the newly learned task, and so on for any number of tasks. Of course, there's limits based on how many we can do, but this is the general setup of what I'm trying to do, or what I mean by continual learning from demonstration. So to do this, we kind of proposed hypernetwork-based models. So hypernetworks are these neural networks that produce the outputs of another neural network. And here, the neural network that is produced by the hypernetwork is something known as a neural ODE. And the neural ODE in this example takes the state of the robot and predicts the derivative of the state. So it's essentially learning a vector field. And the hypernetwork here is interesting because it takes the input to the hypernetwork actually is in the form of a trainable vector, which is known as a task embedding. And this is used to condition the model on the tasks. So let's say this hypernetwork learns 3 different tasks. So for the first time, I will train a task embedding. It will generate this neural OD, and the whole system gets trained end-to-end with supervised learning. After learning the first task embedding is frozen and it's stored. And then for the second task, the same thing repeats. And after learning 3 tasks, it will have 3 different task embeddings that are stored and saved. So during inference, if I wanted to perform the second task, I'll just pick the second task embedding, feed it into the hypernetwork to generate the neural OD for that task. One of the problems with this kind of a model is that all the parameters of this neural OD are produced by the hypernetwork. Sorry?
Sorry, we have a question from the audience.
Yeah, so I was just wondering about the details for the task embedding. So you're creating, like, are those learned or is this type of lookup table? How's that going to work?
Could you please repeat? I missed the first part.
So I'm trying to understand more about where the task embeddings come from or how they are learned. So how are they learned in this end-to-end fashion, or is there a lookup table?
No, there is no lookup table, so they are learned in an end-to-end fashion, and this is just a vector that's initialized in the same way the neural network parameters are initialized. So it's
Okay.
initialized from scratch and trained end-to-end.
Okay, so
Yes.
you're not doing any kind of perception beforehand that's learning a task embedding starting from that model.
No, it's not learned separately. It's learned along with the parameters of the hypernetwork.
Okay, all right.
Yep. Okay, so like I was saying, the hypernetwork generates all the parameters of the neural ODE from the last layer. And this kind of makes this hypernetwork in yellow quite big if the neural ODE is of a certain size. And to counter that, there's another kind of hypernetwork, which is known as chunked hypernetwork. And here, what it does is instead of producing everything from the last layer, this basically treats the weights or the parameters that need to be output as a batched output. So this is very similar to the way we feed in a batch of inputs and we get a batch of outputs with a CNN or something. It treats this generation of neural OD parameters in the same way. And the nice thing about this is that the hypernetwork size itself is quite small, and in some cases it can be even smaller than the network that it produces. Not really going into the details, but I'm happy to answer any questions. Yes, so this is like a variant of this hypernetwork model, and these are the ones that we propose. And as baselines, we compare these two hypernetworks against simple baselines. So the first one is that for every task, so if we are training 10 tasks, we'll just train 10 neural ODs separately and store them. So this is called single nodes or SG. What we could also do is we could gather the data of all the 10 or however many tasks we are learning. And every time we want to learn a new task, we combine the new data with all the old data and do this multitask learning sort of thing. And this we call replay because we are replaying the old data again and again. We could also forget about continual learning and just train a neural OD on the newest data each time, just using fine tuning. And here we would expect it to remember the latest task that's shown and forget the others. And we also compare against some continual learning algorithms that directly try to prevent forgetting inside the neural OD. Again, these are kind of certain family of continual learning algorithms called regularization-based algorithms, but I left out the details because I have to fit in a lot here. So just ask me if you want to know more. Okay, so what we did first in terms of experiments is to compare how continual learning with hypernetworks works on this data set called LASA. So this is a data set of two-dimensional trajectories. So originally they were drawn by humans. Here we use 26 different trajectories, and the task is to learn the 26 trajectories by giving or by training the model one at a time on each of these. So this is a qualitative plot, and on the first row, this is where we use a single node for each task. And here, of course, it does not have any problem in learning it because there's 26 networks for 26 tasks. And the bottom two rows are with the hypernetworks. So the middle one is with the smaller hypernetwork, the chunked one, and the lower row is for the bigger hypernetwork. And here, this is just one hypernetwork that has learned 26 tasks sequentially and is predicting the trajectories for all of those past tasks. And what we see here is that the bigger hypernetwork works quite well, but the smaller hypernetwork, it kind of becomes more and more rigid and has difficulty in learning tasks that are towards the end of the sequence. Another thing that we look at is not just how accurate the predictions are, but also factors such as how well things are remembered from the past or how the size of the model grows with each new task. So for example, with these single networks, I can get perfect reproduction of the trajectories, but then my model size, becomes 26 times the size of a single network, and that's not really ideal. So we have these metrics. In particular, there are 6 metrics here, which are continual learning metrics that look at factors such as how well the past is remembered, how accurate is the overall prediction, how much the storage grows, the size of the model, how long it takes to train, and so on. And then we compare the hypernetworks. So red and green are the hypernetwork, and we compare it with each of the baselines. So this is for the single node per task. And for all the baselines, we see that they kind of fail in one or the other metric. So for example, this one, because it's 26 networks, the combined size of the model is quite big compared to the hypernetworks. And similarly, for all the other baselines, we see a similar trend where they perform well on, a handful of metrics, but always perform badly for the others. This is another data set that we collected by training the robot how to write lowercase letters of the hello world words one at a time. So it was shown one word, one letter at a time, and then at the end it had to reproduce all the letters. And here again, we see that the hypernetworks kind of have a smaller overall model size, remember well without needing to store data of past tasks and so on. Then we tested on some more realistic looking tasks. So here there's a sequence of 4 tasks, opening a box and stacking a bottle and so on. And these were again learned one after the other. And what you see here is the chunked hypernetwork model reproducing all the 4 tasks. So this is just one network that can, when we specify which task we wanted to perform, can reproduce any of the given tasks. Okay, similar picture as before, not really talking about this. But there's a few limitations that we wanted to address. So the first one is the matter of stability. So what we are doing here is that we are learning a vector field of the robot's motion, right? And in cases where maybe the training has not converged properly, or if the initial positions of the robot or the object being manipulated are very different from the demonstrations, it's often possible with neural ODEs that the motion that is predicted kind of diverges away from the goal. And this is a problem. Ideally, we want the robot always to be safe and to converge to the goal. We also saw like the smaller hypernetwork, the chunked hypernetwork, has difficulty in learning more than 8 or 9 tasks. And this gets worse as we add more and more tasks. And this is something we wanted to tackle. The third thing is the way hypernetworks are trained. The training time increases for each new task that is learned. And this is, every time I learn a new task, it just keeps on increasing in this fashion. And this puts an upper limit on how many tasks can be handled. And it's pretty annoying after learning 26 tasks that the amount of time required to train it is quite long. And in the previous work, we were just dealing with lower dimensional trajectories. So, 2-dimensional in the case of this hello world example, or 3-dimensional at the most. And ideally, we want to extend this setup to maybe be able to work with images or latents produced from images. So we wanted to look at higher dimensional trajectories. And this we did in the second paper. And here we rely on this variant of the neural ODE called a stable node. So here, the neural ODE itself consists of 2 different neural networks. The first one on the left is this F theta term, and this is the nominal dynamics model, which is very similar to the neural ODE we saw before. In addition to that, this stable node also contains a parameterized Lyapunov function. And this is actually responsible for ensuring that whatever comes out of the stable node is the motion that comes out of it is actually stable and always converges to a given goal. I'm going to skip this part. This just shows how we combine, how we learn the position and orientation together. It's not very important at this point. But what we do now is that instead of predicting just the parameters of one neural network from the hypernetwork, we predict the parameters of both the nominal dynamics model as well as the Lyapunov network with the hypernetwork using a very similar setup as before. So inside the hypernetwork, nothing much changes. It's just what the hypernetwork produces is kind of different. And we perform experiments again on this two-dimensional LASA dataset. And this is something that is expected, that when we use the stable node produced by the hypernetwork, it does not diverge away from the goal. So on the top row, you see that when we start at initial positions, which are very far away from the demonstration, there's divergence. But in the bottom two rows, this will always converge to the goal and avoids unsafe behavior. But what was really interesting is that the concept of stability is not linked to continual learning. But what we see is that when we enforce stability in this way, the continual learning performance of the model actually increases by quite a lot. So what we show here is the overall prediction errors. So DTW is dynamic time warping error. This just measures how different the predicted trajectory is from the training demonstration. And the right-hand box is just a zoomed in version of these smaller box plots here. What we see is that, especially for the smaller hypernetwork, the chunked hypernetwork, it makes it a lot better when we enforce this stable motion with the help of the stable node. And here we plot the errors after learning each task, and we see that when we use the simple neural OD without stability, it kind of starts struggling after the 8th or 9th task, and at the end is pretty bad. But when we use the stable node, it can learn all of these 26 tasks. Okay. What we did next is to create a data set of higher dimensional trajectories. So LASA was two-dimensional. We take the LASA data set and combine different trajectories to create higher dimensional versions of it. So we created an 8-dimensional, a 16-dimensional, and a 32-dimensional data set, each with 10 different tasks. And when we repeat the experiment on this, we again see that as we increase the dimension of the data, it becomes a harder thing to learn it. But the stable neural OD in terms of continual learning is performing always better than using the simple neural OD. And this is most prominent for the smaller hypernetwork model. And just to show a qualitative example, this is an example of the 8-dimensional case. So each row, let's say for each consecutive 4 boxes, these make up 8 trajectories. So for plotting, I plot them 2 at a time, just to show them. But 4 boxes make up 1 task. And here the chunked hypernetwork has learned all the 10 tasks and is predicting all the past tasks that it has learned. And it can be seen that with the stable node in blue, it's quite accurate overall. Whereas without the stability, there's often problems. There's even divergence in a few cases, which kind of messes up the accuracy of the predictions. We repeat the same experiment on the realistic looking tasks. So here, this is a data set of 9 different tasks. We extend the one from the last paper, and we add a few more to create 9 different tasks. And again, we see that when we enforce stability, the continual learning performance improves in terms of both the position errors as well as the orientation errors. And with one trained hypernetwork model, the robot is able to perform all of these 9 different tasks without much problem. And because this time we have stability, it's also more robust to changes in the initial conditions and so on, which is something that we really want. Okay, I'll try to cover this a bit quickly, but this
That's
is
okay. You might have actually asked a question about the last project or two. I guess, I mean, the hyper networks they're working surprisingly well. And that's at least from my own experience, because there's usually some challenges in getting models like using hyper networks to generalize well. Because there's kind of a magical operation going on there that enables generalization. So like, did you find this, or what do you think you've done, like in addition, to help make, the hyper network enable this type of generalization even better?
So I'm not 100% sure I understand what you mean by generalization. Is it generalizing from, say, images to trajectories, or?
Well, even you just said for that last experiment that it's robust to some changes in the image space. And usually I've found that hyper networks or even some things that are a bit hierarchical don't always generalize that well. They
Okay.
don't, they're not a big fan of zero shot generalization or being able to fine tune, like kind of traditionally.
No, I think in this case, the magic really happens in the stable node, which takes care of the generalizing to different initial positions. Because of this enforced stability thing that, makes sure that even if you start from different positions, it guides it towards the trajectory that's has been seen, or tries to go to the goal. The hypernetwork itself does not, it's kind of separated from the task that is actually performed, right? So once I say perform task 2, I just generate the stable node for task 2, and then it's the stable node itself that takes care of this generalization. So I'm not sure if that answers your question, but it's the property of the stable node actually that is much more important for generalizing in this particular experiment than the hypernetwork directly, because it does not control that explicitly.
Okay, yeah, thanks. That makes more sense. I guess the stable node is doing its job right now for being stable.
Yes.
I guess I was wondering about how this then connects to, like, more out of distribution stability, but that's also covered to some amount in the stable node.
Yes, that's actually, yeah, that's right. The stable node kind of takes care of it. I think the only problem, or what the hypernetwork does, is basically if the training converges, then we can be pretty sure that it can generalize within certain bounds with respect to the initial positions. But if there's problems in the convergence of the training, then I think all bets are off.
Okay, thank you.
Yep. Sorry, my laptop is a bit slow. Okay, so hypernetworks use this equation for learning, and the first part of the loss is just based on the task that's being learned. So this can be something like the mean squared error or something. And the second part is this regularization term that actually takes care of not forgetting the past. So what this term does is that it loops over all of these stored task embeddings and then tries to make the hypernetwork not change its parameters in a way that leads to forgetting. So And this is what actually contributes to this quadratic growth in cumulative training time. So what we do here is we throw away the summation term and we just randomly sample one past task embedding in each training iteration. So by doing this, the time it takes to train or to learn each new task is kind of constant. So the cumulative training time grows linearly. But what we see is that for these kind of robotic trajectories in terms of position and orientation, the performance of the hypernetwork does not really change much. And this allows us to keep on training without increasing the training time. But to be frank, this has its limitations because when we go to these 32-dimensional trajectories, we see that this does not work so well. So this is kind of an open problem. But for the robotic tasks, it's quite fine.
Just to
Okay.
clarify, when you say training iteration, you mean like a mini batch?
I mean, like, let's say I have a certain number of iterations for each task that I'm training, or even if you think of one iteration, okay? So the time it takes to perform that one iteration kind of increases every time
Okay.
because
Cool.
of,
Thanks.
yeah. Okay.
Yeah.
Okay, so if there are any more questions till this part, otherwise I'll just move on. So I've been talking about continual learning from demonstration, which is about learning these different trajectories, each with its own different objective, pouring from a cup or opening a box and so on. And now I'll try to talk about CLNs, where the environment changes without really changing the fundamental task that the robot is performing. And here I'll be talking about this paper called Continual Domain Randomization, where we use continual learning for sim-to-real transfer. Okay, so domain randomization is widely known. So here we start with a robot in simulation, and we identify a number of randomization parameters. Yeah, so if we are talking in terms of images, we can change the color or the brightness, the texture and so on. But let's say in this typical reinforcement learning kind of setup, these are kind of the parameters that we look at. So we look at the latency. This is like introducing delays into the the states, how the states are sensed. We introduce some delays into that. We could introduce some sensor noise. So just adding, let's say, Gaussian noise to the sensor readings. We could randomize the motor torques by changing the stiffness and damping coefficients and so on. So what domain randomization does is that it randomizes all of these different things together in an effort to make sure that when we perform this zero-shot transfer to the real world, all this randomization kind of takes care of the sim to real gap, and then we end up with a model that can control the robot in the real world, and it works well. The problem with this is sometimes if it's a difficult problem to learn in the first place and too many things are being randomized together, it just makes it very difficult to converge to a good policy in simulation. So if it's a very easy task, then sure, we can randomize a lot of things, but based on how difficult the task is, it can get more and more difficult to find a good policy in simulation. And then, of course, it does not transfer so well. So what we propose in this paper is instead of doing this, we can use continual learning to learn the effects of randomizing one parameter or one set of parameters at a time. And when we do this sequentially and use continual learning, it leads to a better sim-to-real transfer. So this is basically what we are doing here. Just maybe try to focus on the colored arrows. Try to set up an animation, but that didn't work. So we start off by training an ideal model in simulation. So by ideal, I mean with no randomization. So this is like a perfect simulation. And we take this trained model, and then we randomize one of the randomization parameters. So let's say we add random sensor noise in the first case. And we use some continual learning algorithm to make sure that whatever has been learned in the ideal training is remembered. We repeat the same process here. And let's say for the second time, we randomize the torque. We add some random, we add something to the joint stiffness and damping coefficients so that the torques are randomized. And again, we use continual learning to make sure that the effects of this one and this one are remembered, and so on. This is how we continue. And the blue and the green are two variants of one algorithm. The details are on the next slide. But this is our setup. And then once all the randomization parameters have been trained on, we transfer the thing to the real world and do zero-shot evaluation. As baselines, we compare against the ideal model. So we just train it in ideal simulation and directly try to control the real robot. We also compare against the typical domain randomization setup where everything is randomized together, and we use that. Or we also compare against this fine-tuning setup where we also follow this sequential kind of paradigm, but we don't try to remember or try to avoid forgetting in any way. So this is just naive fine-tuning. So what we do in terms of algorithms is that we use PPO as the main training algorithm, and we use for continual learning this algorithm known as elastic weight consolidation. So at a very high level, what algorithms like this do is that they say that they try to find an estimate of how important a particular parameter of the neural network is for remembering the past task. And the whole objective is now to make sure that parameters that are very important for previous tasks are not changed as much, and parameters which are not important are allowed to change, thereby it's possible to also learn new things without forgetting the previous things. And in this elastic weight consolidation, they compute this empirical Fisher information, and we use data from the replay buffer to do that. I'm skipping over some of the details due to time, but again, I'm happy to answer any questions. Yeah, so we use EWC, which is the original algorithm, and another online variant of EWC, which is more memory efficient. But the basic learning algorithm and how the parameter importance is computed is kind of very similar. In terms of tasks, we have, let's say, relatively quite simple tasks. So we have a reaching task and a grasping task, and both of these are controlled in the joint space. So the actions are the joint velocities, and the rewards are defined based on how close the robot is to the goal. If the block has been grasped, or if there are collisions, there's some negative rewards in those cases. But the entire setup in terms of learning a task is quite simple, but we make it a bit more difficult by using the joint space, and it's easier to show the sim to real gap in this by controlling the robot in terms of joint velocities. In terms of metric, we not only look at the episodic reward, but we also look at how smooth the motion of the robot is. So this is done by using this thing called continuity cost, which essentially will give a low cost for smooth motion and a higher cost for very jerky motions. And this is something that happens quite regularly for zero-shot sim-to-real transfer if it doesn't work well. Then for the reaching task, we also look at the distance to the target, and for the grasping, we look at how many times. Sorry?
I just coughed, sorry.
Yeah, my audio is a bit off.
There's no question.
Okay, sorry.
Someone has a cold.
Okay. As we say in Germany, Gesundheit. Okay. So the left side, the plot on the left, it shows the training, the convergence during training. And I'll just try to make sense of this plot because it has too many lines. So the pink dotted line that you see here, this is the ideal model that's trained without any randomization, and the orange dotted line is the fully randomized model. And the vertical dotted lines, this shows whenever we change from the ideal training to randomizing the first parameter, then the second parameter, and the third parameter, and so on. And because we start the fine-tuning and the continual learning models by first training on the ideal parameters, these plots start from here. So what we see in this plot is that the fully randomized version kind of takes a little while to converge. It still does converge pretty close to the best possible performance, but it takes a while because of this combined randomization. But the ideal model converges quite fast, as does the fine-tuning model. So in training, everything works very nicely. The ideal model gets very high returns, and everything is fine. But when we transfer this to the real world, we see that, in simulation, the ideal one is the best, but on the real robot, it performs quite badly. And this is the continuity cost, which is also quite high. So, I mean, it's hard to make sense of a table on the slide. So maybe this is better to understand. So if you look at the first force, so this is ideal, this is the fine-tuning ones, and you'll see that on the real robot, there's a lot of to and fro oscillations, and the movement is quite jerky. But the continual learning ones, so the four on the right, the four boxes on the right, these are performing quite well and reach the target without moving about as much as the ideal or the fine-tuning one. For the grasping task as well, we see a similar picture, but here the fully randomized model has a bit more problem converging. So in training, it really doesn't converge to the best possible performance. The ideal model, again, can work very well in simulation, but when we transfer it to the real robot, there's a lot of difference in the performance. One interesting thing here is that the fine-tuning model actually can be really good or really bad based on the sequence in which we train it. So if we know what is the ideal sequence of randomizing different things, if that is known, then fine-tuning works really well. But if we mess that up, if that sequence is not correct, then fine-tuning works really poorly. Whereas the continual learning models kind of have good enough performance irrespective of what is the actual sequence, and also their performance in simulation and reality are not so different. So this again can be seen here, where you'll see the fine-tuning kind of moving around, similar to the ideal model. And also it fails to grasp sometimes, whereas the continual learning ones are much more stable and don't show such a jerky motion. Okay, so that was pretty much it. I'll just end with some thoughts on future work. So for the continual learning from demonstration, we really wanted to extend this by considering vision, because this is one of the major reasons we are even looking at neural networks. Like if I'm only interested in learning trajectories, maybe we don't need neural networks, but with images, it's a different story. So we would want to extend it to work on maybe to condition the hypernetworks based on images. There was also some thought of combining the different motions that are learned with these hypernetworks into a longer sequence of more complicated motions. And this thing where we had this stability improve the continual learning performance made me think that, such inductive biases are also useful in terms of physics. So there's a lot of work in physics-informed learning in robotics, and maybe these kind of inductive biases also can improve continual learning, because for us humans, our intuitive understanding of the world makes it actually easy to learn new things. So this is something that I want to look at in the future. And in terms of the CLNs, the domain randomization work, we also want to extend this. So right now everything is dependent, like the states are numerical states. We want to change this, also include vision and the randomizations we can do with that into this setup. And there's also possibility of combining this with adaptive domain randomization, where the ranges of how much we randomize are also learned or controlled. Okay, and in terms of current work, I mean, this might seem a bit off from everything I've talked about till now, but this thing about inductive biases and how it improves continual learning led me to physics-informed machine learning. So right now I'm looking at intuitive physics and where objects kind of collide with each other, and how knowing the physics or knowing part of the physics of those interactions can actually help the robot perform a task or predict where objects will be in the future. So I'm looking at physics-informed reinforcement learning. And finally, there's a few other things that I'm working on. So grasps and also multi-robot reinforcement learning and imitation learning. So these are a little away from what my core interests are. So I would say what I'm really interested in is like intuitive physics and physics-informed reinforcement learning. And yeah, I hope I was not too boring. That's it pretty much from me. I'll be very happy to answer questions if you have them.
Great. I guess one question I have for you, Sayatan. I noticed in a lot of your results, like there was you make these observations, but I was kind of wondering if you had any sorts of intuitions as to, like the example in the transfer learn, like sim to real experiments you had, like why might continual learning be giving this benefit from the sim to real transfer, where these other methods are failing. That goes kind of beyond just saying like, do we observe that this happened? If you have any thoughts on that.
Yeah, I mean, this comes from our initial motivation for, designing it like this, because when you factorize all the randomization parameters and you learn them one at a time, it's a simpler subproblem to solve, right? And then when continual learning is successful, it means that whatever is learned in maybe this one is remembered in this one. So we are doing two things at once. We are making the problem simpler than what the fully randomized agent is learning. And because we have this capacity of remembering stuff, it just makes it easier to learn. And I think like this incremental thing that we can do with continual learning really helps to accumulate the knowledge over time instead of throwing a big problem at it and trying or expecting it to, learn. So I think this is one of the advantages really of doing this, or maybe why this works in the first place at all.
I see. So I guess you're just like, yeah, I guess I misunderstood when you described it earlier. So you're just saying that you're trying to achieve the same effect as doing randomizing everything, but one variable at a time, and that makes it
Exactly. Yes. Yes.
doing it all together, but learn faster. And
Yes.
okay.
I wonder if you ablated over the order of the parameters?
Yes. So we have like 3 randomization parameters, and there's many different sequences you can do. So what we did initially, I don't show it here, is that we tried to come up with a way of estimating the effect of each randomization parameter. And then we chose 2 sequences based on whether the most important one is at the beginning of the sequence or the most important one is at the end of the sequence. And in our final experiments, we just report these 2 sequences, but yes, we did try different sequences.
And was there a large variability in the resulting performance?
No, for the continual learning methods, no, but for the fine tuning, it does matter what is the sequence that you're using. So,
Oh yeah, for sure.
like, let's say torque has the biggest effect, right? So if you're training on torque at the end, then fine tuning works quite well, because if it remembers torque, it can perform well on the real robot. But if I start with torque, then by the time it gets to the end of the sequence, it forgets. So it's very important, this sequence, the order of the parameters for other methods. And this is one of the things we kind of say in the paper, that with continual learning, you don't really have to know the perfect sequence.
Makes sense.
So I was actually wondering, because in your earlier like pictures for motivation, you were showing a humanoid robot operating in different tasks. So, like, how much do you think this story is going to extend to other types of morphologies? And let's maybe focus on a humanoid like robot.
Yeah, I mean, there's so many papers now that you see like robots doing tons of different tasks, right? So for humanoid robots, I think it's the same kind of problems are true for most robots, right? Like if I'm talking about just a robot arm on a wheelbase or on a humanoid robot. So in terms of manipulation or working with the environment, the challenges are pretty much the same. But for humanoids, when it comes to legged locomotion, I'm not really sure if this same kind of setup is as relevant there. But yeah, I mean, I don't know if I've really answered your question.
No, that's fair. I think it's extrapolating to an entirely different morphology is always going to be a bit tricky. I was just wondering from your experience, or if you've tried other morphologies outside of arms, quadrupeds, or
No, so I have just worked with robot arms, but there is work on different robot morphologies in continual learning. So for example, with wheeled robots, there's quite a bit of at least I've seen a few papers that use wheeled robots for continual learning. And again, like you can think in terms of even if it's a robot dog, this can be something like learning to walk on a smooth surface versus learning to walk on a rocky surface. So a lot of scenarios would benefit from having this open-ended approach to learning. Like I can just start off from what I learned the last time, and I guess different morphologies. It's possible to do experiments with different morphologies as well.
okay, thank you.
Right, if we have no other questions, let's thank our speaker one more time.
Okay, thank you so much.
Thanks again. Take
Thanks
care.
again for taking the time. Good to see you.
Yeah, thanks for inviting me.